So we discussed that traditional condensation physics has been a study of systems in equilibrium, and this is very exciting and interesting physics. There are still many open questions. There is obviously high temperature superconductors, and we'll hear more about insights into these old-standing problems that comes from recent experiments with cold atoms from Emmanuel Fabian. Then Thierry, I think, will also talk about this in connection to one-dimensional physics. And of course, there are topological states, which are very surprising and counterintuitive. And then people can also design new types of systems where they can combine, say, spin-off coupling superconductivity in order to study such exotic excitations as Majorana fermions. And traditional probes, traditional kind of toolbox of condensed physics basically relies on using the paradigm of linear response. It's like a group-point correlation function. It's something that really explores excitations close to the Gauss. And then we said actually what was happening in the last few years is that there was a major push to expand the scope of solid-state physics. And now there are many examples where this paradigm of systems strongly coupled to the path very close to equilibrium no longer works. This includes simply new probes such as resonant X-ray scattering or pump and probe experiments where people think of controlling system parameters in time, or examples of systems which are well isolated from the environment and in which, say, Newtonian can be changed to a very short time scale, these ultra-cold atoms. And so this combination really brings the theoretical challenge of understanding and characterizing the dynamics of many states. And this is a very challenging problem because when we talk about equilibrium and collective modes in equilibrium states, it's actually a very small number of degrees of freedom. It's something that only increases polynomially with the system size. Whereas when we talk about entire Hilbert space, we're talking about exponentially large number, exponentially in the number of particles, which number of particles, of course, theoretically Avogadro's number. So the kind of central theme of what I'll be presenting today is that actually, in many cases, we can make a lot of progress in understanding dynamics by looking at states which don't cover the entire Hilbert space. So we'll use variational states, and the number of parameters still scales polynomially with the number of particles, but I'll try to convince you that even for some paradigmatic systems which we call strongly correlated, this approach can give us reasonable answers. So specifically, today we will focus on fermions, and I'll introduce formalism, and then I'll talk about two specific examples. So one is a Condon model. So for those who haven't seen this before, it's a problem of a localized spin interacting with the fermions through super-exchange interactions. And the second is Anderson model, Anderson impurity model, where we have one level which has very strong repulsion between electrons, and I will also make it more interesting by adding phonons, so it will be a combination of strong electron-electron interaction on one side and electron-phonon interaction. And in fact, this is not just sort of, and I'll try to connect both of them to real-world experiments. Well, Condon problem probably is very well grounded in many systems, and to mention a few of them. In this case of Anderson-Holstein model, I'll focus on very specific recent experiments of terahertz STM. It's a combination of STM experiments which give sort of nanoscale resolution with some kind of terahertz technology which allows to control properties of matter on the scale of picoseconds in femtoseconds. Okay, so let me start by giving you some general introduction. And I want to point out that the way, very often, when we think about finding the ground state of some complicated interacting systems, we can also analyze it as a problem in dynamics, except in this case, dynamics that we need to look at is dynamics in imaginary time rather than real time. So let me explain you how this works. So imagine that I have a generic interacting system, right? And I start with my arbitrary state, which I can decompose in terms of eigenstates of my system. Right? Now, what we can do, we can evolve this state, this arbitrary initial state in time, if we have decomposition in terms of eigenstate. It's very easy how it goes, right? Because every eigenstate just gets exponential factor which depends on the energy of the state. And then we realize that the state which sort of remains largest, which has sufficiently long time, is a ground state, because all states decay exponentially, and the state with the lowest energy will actually sort of have a finite amplitude longer than all the other components. So therefore, if we take arbitrary initial state and then evolve it in imaginary time, as long as this initial state had a finite overlap with the ground state, the main contribution that will be left at long time will be the ground state. So therefore, of course, if we just look at this component, it's not normalized, so we have to normalize it properly, but that would be sort of a generic recipe. If we want to find the ground state, let's just evolve in imaginary time, add this factor for normalization, and that will be the ground state. So unless we're very unlucky and chose a state which has exactly zero overlap with the ground state, this should bring us to the ground state. And this actually we can formulate also as a differential equation, right? Because we say, okay, so we know that we have to evolve this in imaginary times, time going to infinity. Let's think about evolution of the state, right? If that's the state that we want, let's just differentiate with respect to this tau. So we get tau, of course, comes in the numerator, so we get Hamiltonian in front of it. We also have tau in normalization factor in the denominator, right? We would differentiate the denominator, right? We get the same factor in the numerator. So that's the expression which we can actually rewrite after some very simple algebra the following way, that the time derivative of the state in imaginary time is simply the Hamiltonian h minus the expectation value of h applied to the state. So what you want to do then is simply solve the differential equation in imaginary time, let the state flow until it comes to a fixed point, right? Because so this procedure will sort of keep lowering, if we can think about it as going to a state that has a smaller and smaller operational energy, and when it saturates, right, then that's when we are in the ground state. Okay, so so therefore, like in many things that I'll discussing later on, when we need to start by finding a ground state, even though we're interested in dynamics, we have to usually start dynamics with a ground state. To find this ground state, we will use generalization of this velocity variational wave function. And now let me give you also a general perspective on how exactly we understand variational dynamics. So this idea actually goes back to Dirac, and the general principle is the following. Okay, so we have, like as I said, Hilbert space is so rich we cannot possibly try to access all states in the Hilbert space. So, however, we think that, say, the ground state or states involved in dynamics, they belong to a certain family of states, right? And let's say we can parameterize this family of states by a collection of parameters, which we call cycling, right? And let's, so schematically, if I think about this variational family of states, they give me some manifold, which is shown here. And now what we want to do is we want to look at dynamics. If I start, let's say, in a state which corresponds to my variational state, and I want to evolve it in real time, we mentioned it. And then, so we know that basically, if you think about the usual Schrödinger equation, right? So we can write I d psi over dt, right? This h psi. So we can say that psi of t plus dt, right? This psi of t plus 1 over I h psi of t delta t, right? So this is my change in the wave function, which occurs during time delta t. And well, if I do this exactly, right, if I look at this change of my wave function, if I look at delta psi, generically, this change of wave function takes me outside, away from my operational manifold. But, you know, we give up on trying to find the exact solution, so we say we want to project this change of the wave function back into this variational manifold. And of course, projection for infinitesimal changes in the wave function means actually projection onto the tangential plane of our variational manifold. So how do we do this projection? Well, what we have to do, we have to define basis vectors in the variational manifold. Right? And so we find these basis vectors just by simply taking derivatives of the variational wave function with respect to parameters, and then basically sort of we can think about it as orthogonalizing, finding the overlaps between these vectors. And then when we look at the change of the wave function, right, along the variational manifold can be parameterized in terms of changes of these parameters psi, right? So yeah, it can be, as we said, evolution either in real time or evolution in imaginary time. And you can immediately, and as we discussed in the case of evolution in imaginary time, what comes in is a Hamiltonian minus the expectation value of the Hamiltonian, which is energy. So we look at this variation of the wave function, but then we have to project it into basis vectors in our tangential plane, and that gives us really variations in parameters. So therefore, variational solution of the Schrödinger equation reduces to some kind of differential equations for parameters on our variational manifold, and in order to do this projection, in principle, we have to go through the steps of calculating basis vectors, Gram matrix, and so on, but they sort of have this very general structure, and we'll see specific examples how this works. Okay, so what we're discussing today is something that you have seen before, and this is really mean field approximation, but with a twist. Right? So and I'll focus really on fermions. So let me first remind you kind of two cases of mean field approximation for fermions that you have seen before. Partially, I also mentioned a couple of these. So probably this one of the first things you learned in condensed classes is the Hartree-Fock equations. So it's an idea that when we want to solve a problem of interacting electrons, we make a simplifying approximation that an anybody's state is a slightly determinant of single particle wave functions. Right? It's really the simplest type of anybody wave function you can construct. You just have to find the best single particle state and make a wave function which is totally anti-symmetric with respect to this single particle state. Right? And the goal then in the Hartree-Fock approximation is reduced from really solving for the many-body wave function to solving for single particle wave function. Right? And the way these equations are formulated is basically looks like that. So when we want to compute the single particle wave function, obviously there is kinetic part with external potential, and then there are these two pieces, right, which we call Hartree term and the Fock term. And let's say the Hartree term is very easy to understand. It agrees with our classical intuition. So we know that we have interaction between electrons, let's say at point r and r prime. So basically, this gives us a contribution to the electron density at point r prime due to wave function L. So we have to sum over all occupied states. We find the density at point r prime, and that corresponds then with its non-local interaction, such as Coulomb interaction, to an effective potential at point r. And there is an exchange term, right, which is somewhat more tricky. You can see that the wave function at point R, right, actually depends on itself at a different point, and also wave functions, other wave functions in the system. So this arises from the fact that we take a slightly determinant state, which is completely anti-symmetric with respect to this change of both the particles. Right? So basically, this becomes a kind of a nonlinear, self-consistent equation for single particle eigenstate. Okay, so this is the first example. The second example of well, you have seen mean field approximation is, say, when you talk about superfluid state of bosons, right? I remind you the usual Bogoliubov wave function for weakly interacting DC. So we have a condensate or macroscopic condensate of atoms at k equal to 0, but we also have quantum depletion. Right? We also have pairs of bosons which combine into this kind of zero central mass combinations, and then Bogoliubov theory just sets up explicit equations for, let's say, quantum depletion. So we'll discuss this and problem and its extensions in the next lecture. So what's more relevant for us today is the BCS theory, and hopefully it's something that you guys have seen in your solid state classes, right? So it's an idea that when we have pairing in the electron system, the wave function has this very simple structure. It's a product over different states, where state with momentum k and spin up and momentum minus k and spin down is either both of the states are unoccupied or both of the states are occupied. So this is the celebrated wave function. And I also remind you that actually the same wave function can also be written as an exponent, right? And the way to see this, right, if we simply write the wave function, let me just take one term, b of k or q of k, c of k, dagger c minus k down dagger. Let's start expanding this. So the first term obviously is 1, then the next term is b of k, u of k, c of k, so minus k down dagger. Then there will be 1/2 u of k, c of k up, c of minus k down dagger squared, and so on. So I claim that we can actually limit ourselves to just the first two terms, and we can throw all the other terms. Is it obvious why? We're trying, these are fermionic operators, right? We try to create the same, apply the same creation operator twice, we get 0. And so therefore we know that all of these terms and higher order terms will go to 0, and therefore this exponent really reduces to just this intuition. Right? And that's really what shows the connection between this perhaps more familiar way of writing the BCS wave function in terms of use and this exponential form. Okay, so what we will do today is generalize this construction to more, use the same philosophy, but in a more general setting. Questions? Okay, so let's start with fermionic Gaussian states, and I'll give you sort of perhaps a more modern perspective on Hartree-Fock, but also on this BCS wave function. Actually, let me start with a very simple example first. I'll really consider just two states. Like imagine that I live like it's fermionic space in which I only have state 1 and state 2. And then we do the following. So in some sense, we try to construct a generalization of this BCS type of wave function. So we say, let me consider a state which I want to be a superpositional state when, in which there are no fermions, or I have both fermions occupied. Right? Again, remember, it's exactly what we saw in the case of BCS wave function. Right? We saw a state which looked like u of k plus b of k, c of k up, c of minus k down dagger, right, acting on vacuum. So we had a finite amplitude we had a superpositional state in which there were no fermions, right, or a state in which we had two fermions simultaneously. Right, so in the spirit I write a state, right, which is cosine theta, no fermions, and sine theta where I have two fermions. I'll keep this sort of example simple. I'll not add phase factors, they can all be included, but let's just do sort of very basic demonstration. Okay, so if we look at this state, right, just at this wave function, we can then ask, well, what are the expectation values which characterize it? Well, obviously we have expectation, we have just occupations of fermions, right? So how would we compute them? Well, if this is our state, right? So we said our state theta, right, is cosine theta empty, right, plus sine theta C1 minus C2 vector. It's an empty state, and then we want to compute theta, right, C1 dagger C1 theta, and we can write it as basically vacuum. We have cosine theta plus sine theta C2 C1, right? So that's basically my theta state. C1 dagger C1, then I have cosine theta plus sine theta dagger C1 dagger, right, vacuum. So clearly the only contribution arises to the occupation number from the part of the wave function that has a C1 fermion, right? So therefore I have to have sine theta here, and that's why in the expectation value we get sine squared. The state also has a more unusual expectation value, although it's something that you hopefully again remember from your study of superconductivity, that in the state theta, right, we have an expectation value of the operator C2, C1, right? And the way to see this is, again, it's a superposition, right, of an empty state, cosine theta plus sine theta C2, C1, right? And now we have to one of this C2, C1, C2, C1 cosine theta plus sine theta. So I'm confusing all my equation annihilation, so this is brass, so therefore it should be like this, and then we have C2 dagger, C1 dagger, and right, so you can see that in this state, I start with a vacuum state. Right, so this is my vacuum state, and I create two fermions. Now I annihilate fermions, and then I have to take an envelope, but of course after I create it and annihilate it, then I have a vacuum state, therefore I only get an envelope with this vacuum state. But so this, therefore the contribution really arises from the crosscut from the part which had two fermions and the part which did not have the fermions, right? So it's cosine theta, sine theta. So these are really the two types of expectation values that characterize the state. Okay, and now what I want to show is that actually there is a more convenient way of thinking about the state in terms of applying a unitary operator. So let me define, what I want to argue is that the state which we just introduced can actually be defined as this unitary operator acting on vacuum. And this unitary operator, you can see, is that actually it's a combination of pair creation operator and pair annihilation operator. But firstly, we want to demonstrate that this is a unitary operator. Well, to do this, right, what we want to show, we write this operator as a exponent of another operator S. And what I want to show is that the operator S is, when we take Hermitian conjugate, is minus itself. And lambda in our case is a real parameter. Right? Well, it's very easy to check this, right? If I take my operator, pair creation, pair annihilation operator, I do Hermitian conjugate, right? I get C2, C1. So you can see that it's the same operator as we started with, except the order of the fermionic operators has been exchanged, so we get a minus sign. right? Therefore, okay, it's clearly a Hermitian operator. Therefore, if I take exponent of this, the real prefactor, it is a unitary operator. Okay, possible. Which, of course, and the reason I want unitary operator is that if I start with a normalized state, which is a vacuum, I apply unitary operator, it preserves the norm, right? So I don't have to normalize my state again. And now, actually, what I want to show is that, okay, we define this unitary operator, and we define now a state, which we get just by applying this unitary operator on the vacuum, that if we compute expectation values exactly the same as we discussed before, right, for the BCS type state, they will have this structure. So how do we do this? So in order to check this, actually, no, I will use a trick. Right? So here I think about this operator really applied to the state. That's how I define my Gaussian state. But I can flip it around and instead talk about this unitary operator applied to creation and annihilation operators themselves. And you can very easily let us now check that in fact that a very simple transformation of this fermionic annihilation and creation operators, which again looks, to those of you who remember BCS theory, looks exactly like BCS transformation of the operators. So how does this work? Okay, so this is our unitary operator, right? It's conjugate, and now I sandwich my operator C1 between the operator U and U dagger. And what I will do now is I will simply take the derivative, right? So I have this C1 lambda, right? I take its derivative with respect to lambda. But lambda comes in only from the point of view of the U operators, right, on the two sides. So, right, so we have C1, right, of lambda is e to minus lambda C1 dagger, C2 dagger, C1, C2, right, we have C1, and then we have e to lambda C1 dagger, C2 dagger plus C2. So when we write dC1 over d lambda, I differentiate with respect to lambda, so this expression comes down from the exponent, right? So I get e to minus lambda, this expression, and then I'll have C1 dagger, C2 dagger plus C1, C2 times C1. And then if I differentiate with respect to lambda, also on the right hand side I have operator U. So, okay, and this comes with a minus sign, right? So I have minus this plus, now C1 is on the left, C1 dagger, C2 dagger plus C1, C2. And then I have e to lambda, and again this. So, okay, but this, you can immediately see is nothing but the commutator of C1. So therefore, what we're left with, we have this U dagger commutator, right, and then U on the right. Because this commutator is very easy to compute, we just get C2 dagger. So there, and so now what we are left with, the derivative of C1 operator with respect to lambda is now C2 dagger operator sandwiched between, again, the same kind of unitary operator and its conjugate. So therefore we have, and that's what we would call sort of, again, lambda transformed creation operator C2. Therefore we get, closed set of equations, dC1 over d lambda becomes C minus C2 dagger of lambda, and dC2 dagger of d lambda by the same calculation becomes C1 lambda. So, okay, and so we have differential equation on these operators, and we know the initial condition that when lambda is equal to 0, C1 of lambda should be just C1 itself, right? Because if lambda is equal to 0, the unitary operator just becomes an identity, so C1 goes back to itself. And you can immediately see that on the solution to this differential equation with the boundary condition that when lambda is equal to 0, C1 of lambda is equal to C1 and C2 dagger of 0 is equal to C2 is just simply this transformation. Again, so that's how we see how this unitary operator acts on the operators, right? So we. Okay, and now calculation is very easy. Let's say we have this state lambda, right, in which we want to, and of course the state we define through these unitary operators, but we know that usually Dagger gives me identity, I can always insert it in the middle. And then what I'm left with, as you can see, is simply this transformation of C1 Dagger operator and transformation of C1 operator, and then I will have to calculate expectation value in vacuum. Right, and this transformation we just worked out, and now taking expectation value of the operators in vacuum is very easy, right? If we try to annihilate the vacuum, we'll get 0, so we only get the contribution when we add the fermion. When we annihilate the fermions, we get sine squared 1. So we can go through the same trick for all other expectation values, and we can very easily work out that in our state, right, defined through this Gaussian transformation lambda, expectation value sine squared lambda cosine lambda. Sine lambda. And what, as we said, actually what we want to do, we actually want to find the correspondence to this other state, PCS-like state, which was a superposition into vacuum and into fermions. And by simply comparing the expectation value, we realize that, well, what actually we have is that this state, right, PCS-like state, which is a superposition of cosine, sine times double occupied, can be written as an exponent, right? Okay, so now let's try to generalize this to the case of many fermions, right? So for two fermions, this was simple. The construction is actually is as follows. So now I use kind of certain, again, mathematical trick, but again, it just simplifies the notation, but it's not fundamental. So we start with Dirac fermions, so now I don't have just two, I have many of them. And let me simply decompose every Dirac fermions into Majorana, sort of a couple of Majorana fermions. It doesn't mean that they have true physical excitation to Majorana. It just makes formulas easy, because now these are kind of real fermions. And so from the usual commutation, anti-commutation relation for the C operators, we can derive anti-commutation relations for the Majorana fermion. We also know that they square to 1. And now we, okay, and so then just again to emphasize that it's really just a change of language, right? So I can either represent sort of my operators in terms of Majorana fermions, and I now have 2n of them, or in terms of creation and annihilation operators for the original Dirac fermions, and there is just a linear transformation that relates to the two. So, okay, and now what I do is actually something which generalizes. Remember, in the case of two fermions, we said, well, the transformation that I want, right, I could write as it was e to minus theta C1 dagger C2 dagger, right, plus C1 C2. It was basically an exponent of the, was an exponent of something which was quadratic in fermions. So now I have n fermions, but I will introduce the same structure, right? So I'll take the operator to be exponent of quadratic form of the operators. Now you can think this A, as you remember around the fermions, that they have 2n components. So this matrix is 2n by 2n. And and the convenience of using Majorana fermions is that now sort of creation and annihilation operators are treated on equal footing. And you can also very easily check that this is again exponent of that this operator is a Hermitian operator, right? I remind you that also another way of thinking about unitary operators, if I write e to I O, but O is a Hermitian operator, right? O dagger is equal to the operator itself, and if I write U dagger, right, it will be e to minus I O dagger, but O dagger is the same as O, so e to minus I O operator, and therefore it's basically U to minus 1. So therefore it is a Hermitian operator. So you can very easily check that as long as this matrix psi is anti-symmetric, this operator is a Hermitian operator. And therefore, exponent Hermitian operator is a unitary transformation. And obviously, it's just kind of like a generalization of what we did for two fermions. And we can now define a Gaussian state as just this Gaussian transformation acting on vacuum. And we can also check, remember we talked about transformation of fermions. Remember, I think we still erased them, but we had this transformation of, let's see if we, for the two fermion case, we said that if I apply U dagger C1 U, we get C1, let's say, cosine theta plus U dagger sine theta. Exactly the same structure applies now in this more general case. If we apply this unitary operator on the two sides of our fermionic operator, it actually it is some linear transformation of different fermionic of the original Majorana fermions, where there is a matrix U, which gives us a transformation, which is exponent of the matrix that we have in the unitary operator itself, which is sort of like, remember, in the wave function we have theta, and in the transformation we have cosine theta. Now you're not surprised that we see something like sine. So this multi-component case is actually exactly the same as what we saw in the simple calculation for the two fermion case. Okay, and so now what we can do is we can, as we said, define this general Gaussian state, right, which is this Gaussian transformation acting on vacuum. So now this is our generic definition of Gaussian state, and it includes lately determinants, it includes BCS wave function, it includes states such as like spin and charge density wave states, and you can see this just by saying, oh, actually, like in this state, what kind of expectation values do I have? Well, I can just take quadratic operators, expectation value of any quadratic operators, and I can express them exactly in terms of this transformation matrix, gamma. Right? Again, it's very similar calculation how we computed, say, expectation value. Remember, in the two-case example, we said, okay, let me look at states lambda, and I want to calculate C1 expectation value. So then we wrote this as U dagger C1U, U dagger C1U, right? And then acting on, again, vacuum. So this was our and then we said, oh, this is really our C1 dagger of theta. This is our transformed state. This is our transformed state. And we just had to calculate expectation value of these operators. Transformed operators, which we said this was cosine theta, right? C1 plus sine theta, C2 dagger, right? And so it's not surprising that we get very similar structure, right? That basically, we said this operators U, right? They define for us transformation of single particle operators. So if we calculate expectation value, we get essentially something which is sort of this U, right? Is exponent of what is in the wave function. And just as before we were getting cosine squared theta or cosine sine theta, the same here we get U times U, which will it's like cosine squared or sine squared theta. So really, like if we understand the example with just two fermions, the case with many fermions is just a matrix generalization of what we saw in the case of two fermions. So, and now, like physically, we understand that this can be expectation value of, again, of the occupation operators. We can talk about, say, CI dagger, CI expectation value, or let's say with the same spin, or we can talk about, let's say, spin up, spin down expectation value. Gaussian. Therefore, these states can describe states with broken spin symmetry. They can describe also superconducting states. Right? If we add, say, two creation operators. Right? Again, this expectation value is encoded in this Green's function. Okay, right, and let's say we can either characterize our state in terms of expectation values of this Majorana representation or operators in Majorana representation, or in terms of the original creation annihilation operators. They're just linear transformations. Okay, and now the simplest thing we can do, because we already have a fairly large family of states, right, these Gaussian states, And so we can try and describe dynamics using this Gaussian state. And the procedure is, as we said, is to reduce dynamics into differential equations for parameters of this variational wave functions. In our case, what this means is actually it would be to reduce dynamics to parameters which are this side, but actually it turns out that for many practical purposes it's easier to just use fermionic expectation values, right? Really, expectation values of creation annihilation operators. Okay, so fortunately, at this point, right, I have to cheat, right? We have limited time, so I will not go through all the steps how to do this kind of projections to the tangential plane on the Gaussian states. Perhaps, depending on how this lecture goes, in the next lecture I'll show you very similar derivation for bosons. But what I want to, so I'll just state the result, that when you do this projection, it turns out that dynamics in this Gaussian state becomes very simple matrix equation, right? So remember, this gamma is really a matrix of correlations encoded in this Gaussian state. And if we want to look at real-time evolution, we get a differential equation where this h is simply expectation value of the Hamiltonian with respect in terms of this correlation matrix. Or if we want to calculate imaginary time dynamics, dynamics which takes us to the ground state, we have to evolve this correlation matrix gamma, right, by solving this differential equation. And this is a nonlinear differential equation for general interacting Hamiltonian because this energy as a function of correlation matrix can be a complicated function, but still we dramatically reduce the complexity of the problem, right? From a complicated quantum problem, we simply have to solve nonlinear differential equation. Okay, so now what of course I need to show you is that this approach can give some non-trivial physics for challenging problems. So the problem that we'll discuss first is the Kondo model. So for those of you who haven't seen this before, I'll just give a brief overview. So it's a model where we have a batch of fermions, right? I keep it very generic, right? It can be, let's say, electrons on some lattice that may be disordered in any dimension. I have an impurity spin, right? And then this impurity spin can couple to fermions, right? And it's easiest to think about, let's say, if this n, let's say, is an index in real space. So let's say if coupling, let's say if this coupling G is only at site n equals to 0, then this is something that corresponds to tradition. Basically, it's really, it would be coupling with the impurity spin. So let's say the usual Kondo interaction in condense method looks like spin of the impurity times psi alpha dagger of 0, sigma psi beta of 0, and this is r equal to 0. So 0 stands for r equal to 0. It's really local interaction between spin of the itinerant fermions with the impurity spin. But there are problems where we have to look at non-local interaction. It actually arises in the context of cold atoms, like say Rydberg dynamics of Rydberg excitations. If anybody is interested, we'll be happy to discuss this as a project that Haseem and I are working on now. But okay, actually, our discussion will be sufficiently general. And historically, the problem of Kondo interaction came when people tried to understand strange behavior resistivity of metals with magnetic impurities, and they realized that actually it really arises from this interaction of localized spins with itinerant electrons. Kondo interaction underlies a whole class of materials called heavy fermion materials, where now you have not just not just a small density of those impurity spins, but a lattice of impurity spins. And then people also realize that it plays an important role in mesoscopic physics in transport, and we'll see some aspect of this later today. And I want to emphasize that Kondo problem is extremely non-trivial, so it's often believed that you you cannot analyze it using the usual impute approximation. In fact, the most common way of thinking about it is using renormalization rule. So Thierry already started introducing you the concept of renormalization rule, but roughly the idea is that we try to eliminate higher energy degrees of freedom and see how effectively Newtonian changes as we describe low energy degrees of freedom. And if we parameterize this in terms of interaction, I'm not saying we can talk about interaction, so let me decompose it, interaction in terms of JZ, SC, impurity, right? Psi alpha, dagger 0, sigma Z, psi beta 0, plus J perpendicular, and this would be SX impurity, psi dagger sigma X, psi 0, plus SY impurity, psi dagger of 0, sigma Y, psi of 0. So we basically give different strength of interaction for the Z and for the XY components of the interaction. Then what one can show is that even if one starts with, if we start with JZ equal to J, okay, sorry, what in this notation, what I call JZ is actually J parallel. Sorry, this terminology of J parallel and J. So if we have SU2 symmetric interaction, that really means this line. So we can start with very small interaction, and as we do our J procedures, we describe systems at low and lower temperatures. Actually, this J's become larger and larger. This corresponds to the formation of the Kondo singlet. That's the canonical Kondo effect. But then you know that you can also start with more exotic systems, say in which J's are ferromagnetic, right? So then you can start with J ferromagnetic. However, J perpendicular is larger than J parallel. We can start here. And then what we will find is that the system, even though it has ferromagnetic to begin with, because of the anisotropy, as we do our G, we'll end up making a singlet configuration. Right? And that is really something that is very counterintuitive, and like in the RG appears as parameters get renormalized as we're getting so low energy effective model starting from the microscopes by integrating out high energy degrees of freedom. So, okay, so if we try to do kind of like a very brute force approach, just do Hartree Faulkner the Kondo model, well, we will fail because actually we know that the ultimate fate, let's say in the antichromatic phase, is a singlet, right? So impurity spin doesn't really have expectation value. It's very strongly entangled with the fermion path. So we have to do something more creative. So let me show you how to, so what we will do now is before we apply mean field, we'll actually do a trick, right? It's actually, the trick is, comes from thinking about impurity models, and the idea is to go into the frame, like in some sense you can understand it as trying to get rid of the impurity degree of freedom, right? To make it, to turn it into a kind of soft quantity. And so here is the idea, okay, so this is our Hamiltonian, right? Again, our fermions, our impurity spin coupling, right, between the impurity spin and the path fermions. And now let me define a parity operator, which is conserved for the system, right? It's really an integral of motion. The way to see why it's an integral of motion is to see the basic, okay, so I have sigma z for the impurity, but sigma z for the impurity is simply rotation by pi, right? You see, like the spin of the impurity, spin 1/2, is 1/2 sigma z impurity. So it's really this sigma z impurity is simply rotation by pi of the impurity spin. And on the other hand, this parity operator, right, for the spin out fermions in the path, I can really rewrite as, you know, again, it's equal to I pi over to n up minus n down, but this 1/2 n up minus n down simply is SZ of the path. So here I have some extra piece, but it involves a total number of fermions which doesn't change, so it's just a C number. So basically my parity operator, right, is a simple rotation of the system around this the z-axis by pi. And that's a symmetry of the Hamiltonian, right? So the fact that it's a symmetry simply means that the commutator of the Hamiltonian with this operator must be 0, right? This operator is conserved in dynamics. And on the other hand, this is an operator, right, which, okay, here, oh, it's an operator, right, which has eigenvalues +1 and -1. Again, it's very easy to see, right, because sigma z in impurity can be +1 or -1, right? This parity operator, if I have even number of fermions with spin up in the bath, it's +1. If I have odd number of fermions, it's -1. Therefore, this operator is always a product of plus and -1, and so its square will always be +1. So it's an operator, this parity operator, which it has eigenvalues -1 and +1. It squares to 1, and that is very reminiscent of one of these components of like one of the Pauli matrices, right? That sigma x, right, has eigenvalues plus or -1, and it squares to 1. So I did. Now, what I want to argue is that actually we can use this fact to come up with again a unitary transformation, which maps these conserved parity operators into the impurity, right? And that's actually this transformation explicitly. The idea is as follows. So why we want to do this? Because it's an exact transformation. Right? It doesn't change the system. But I know that before that, in terms of my original variables, this parity is conserved and commute with the Hamiltonians, and after the transformation, my sigma x of the impurity will be conserved. It will commute with the Hamiltonian. In this trick, I will actually manage to get rid of the impurity in a sense that its spin will no longer change under dynamics. There will be a price to pay, as you will see, but still it's a way of entangling the impurity with the fermion in the back. Okay, so how do we do this? Again, it's a matter of very simple algebra, right? So we have our transformation, which is just a parity operator for the bath. Then we have sigma of impurity. And we just send, so to understand how it affects the parity operator, it involves, let's say, sigma z of the impurity. So let's just see how this transformation acts on sigma z of the impurity. Well, at this point, it just becomes an exercise with Pauli matrices, because this pz, right, it only acts on the bath, it doesn't act on the impurity. So it really, so we can effectively take it out. Well, not really take it out, we should still remember that, let's say you see, we can have a term which is pz times pz, but pz squared is just 1. So we just have to keep track of the order of sigma y and sigma z operators. So we have a single pz, then we can have sigma y and sigma z first, or we can have sigma z and sigma y first. So it becomes a commutator. So when the dust settles, right, you can see that the transformation of sigma z is just sigma x impurity times the parity operator for the bath. And then for the parity operator, again, we apply this unitary parity of the bath, right? This pz is really rotation by half just of the bath itself without the impurity. And we can, now this parity, right, commutes with this spin operator of the impurity, and we just need to use the fact that now we will have this parity cube, but parity squared is 1. Therefore, actually, this pz operator goes into itself. So, and therefore now, okay, so we have this transformation for sigma z impurity, we have transformation for pz. So our total parity operator was a product of the two, right? We apply this, we say sigma z itself becomes sigma x impurity pz goes to itself. So therefore, when we apply, basically it means that the unitary transformation acting on the total pz just gives us sigma x of the impurity, just as we promised. So, okay, the rules are fairly simple. You can then check how other operators transform. And then, after this unitary operation, we end up with the Hamiltonian, in which if you look at it, at the interaction with the impurity, there is only one spin component of the impurity left, which is sigma x. And that's exactly what is required, because we said that sigma x will have to commute with the transformed Hamiltonian. Which means we can no longer have sigma y of the impurity in the Hamiltonian, because it does not commute with sigma x. So just the fact that we design the transformation in such a way that sigma x we commute with it guarantees that after the transformation, all we are left from the impurity degree of freedom is just sigma x. And of course now, because sigma x is commutes with the Hamiltonian, we can just say, oh, if we prepared our system with sigma x equal to +1, -1, it will just stay there forever. It really is now an integral of motion. Okay, well, it looks a bit like kind of surprising. Are we getting something for free? Because we started by saying, oh, it's such a complicated system, spin is entangled with the fermions, but we do a transformation and now spin is conserved. Well, the price that we pay is that we actually generate very complicated interaction between the fermions. Right? So, because I remind, like, for example, we have this p path, right, and that's the same as this pt. It's exponent of something which is quadratic in the fermionic operator. So, therefore, this this p path, right, is basically e to I sum c and to dagger c and pi, right? So if I expand, right, of course it has terms which are quadratic in c plus terms which are sort of fourth order and so on. So we have sort of infinite order interaction in formulas. So we started with electrons which were non-interacting, but they interacted with impurity spin. Now we decoupled the impurity spin, but we generated a complicated interaction with the fermions. So trying to do something analytically for the fermions would be very hard. But our philosophy is to do variational state, right? So then what we do is say, well, okay, now it's just some complicated Hamiltonians, but in fact, if we're doing variational wave functions, in many respects, how complicated the Hamiltonian is doesn't really matter as long as we can calculate expectation values of this Hamiltonian, say using Gaussian state, we're in business. You can just write the ends. And that's exactly what you can do. So you can say, well, let me assume that my fermions in the Gaussian state, right, which I can parameterize by this. Remember, we have this gamma matrix, which really describes all the expectation values of the operators, right? It basically encodes, right? So gamma ij is really just expectation value of ci cj. So we have this. Gamma matrix. We have this interaction, which is exponent of quadratic form, but it turns out that it's something that you can still evaluate relatively in a straightforward way using Gaussian states. It's basically weak theory, because okay, explain this, but you can show that all the higher order correlation functions for Gaussian states can be written in terms of two-point correlation function, in terms of the same Gaussian. So the expectation out of the path, okay, it becomes a factor of this gamma matrix. Okay, it's unpleasant to compute numerically, but still quite possible. And so now to find the ground state, all we have to do is just solve this nonlinear equation for the parameters of gamma. Okay, and now I can just show you the results. Remember, we said that Kondo problem is rather non-trivial, right? It's like people believe that you need to use RG or beta ansatz to find the ground state. Now let's check what our Gaussian state solution gives. So let's say the way we will check it, we will look at correlations between the impurity spin. But remember, we have interaction. So we have interaction J, right, which can be ferromagnetic or anti-ferromagnetic. So what we will check is really correlation between the impurity spin and spin of the fermions at the position of the impurity spin. And if we have anti-ferromagnetic interaction, right, they should be anti-aligned, right? So this is actually this point 2. So right triangle, indeed, we see negative correlation. Okay, the anti-aligned. Then we take, okay, so point 1 is when interactions are ferromagnetic. Okay, so we get ferromagnetic interaction. And then, but then there is this point 3 where we start with interaction which is actually ferromagnetic to begin with. But then as a result of this RG flow, the system should end up being anti-ferromagnetic. And interestingly, this later determinant gives us exactly that. It gives us anti-ferromagnetic relations inspired by experiments which can be done in experiment in Imanova blocks. I will not explain all the details. It's using alkali growth at terbium atoms. One can do interesting quench experiments. So I'll basically, what matters to us is that one can prepare a system in which you have this very exotic anisotropic ferromagnetic interaction. So the ferromagnetic, but they should flow towards the anti-ferromagnetic regime at low energies. And so what one can do in cold atoms is you can start with an impurity spin being decoupled, and then you suddenly introduce coupling of this impurity spin to the bottom. Right? And then we want to ask, so how do correlations develop, right? Because to begin with, we start with impurity spin and fermions being completely decoupled, but then they start getting entangled. And okay, so I'll just show this part. That's really this regime. So what you see that at short distances, this color, it sort of encodes correlations. So, and this is a function. So as we go up, this is time, this is position. So we start, so you see the light cone, basically correlations propagate as we switch on coupling to the impurity, they develop, extend over a longer range. And at first, they're ferromagnetic because that's this blue color. And that simply tells us that the microscopic model was ferromagnetic. But then eventually the system recognizes that it should flow towards the anti-ferromagnetic ground state, and you see the sign of correlation actually changes. So in fact, this kind of variational wave function captures this complicated dynamics which is happening in real time, that the system discovers that low energy degrees of freedom should actually be anti-ferromagnetically coupled rather than ferromagnetically, and we see this from the Gaussian state. So, see how much time? Sorry.
Minus 2 minutes.
Minus 2 minutes. I see. Okay. So I guess then we'll have to talk about the Anderson problem in the next lecture. And let me just summarize that in this case, like in this specific case, we see that variational state, even though it has far fewer variables, right? Basically, we're just talking about 1,000 compared to kind of billions, 10 of billions, which exact MPS on the matrix product state requires, can get essentially the same answer. So if we design our variational wave functions cleverly, we can get the correct physics, correct description of our system. Of course, what was important for the Kondo problem is that we didn't try to apply the kind of Gaussian answers to the original microscopic model. We had to use the trick of entangling the impurity and the fermions first, but after that, just doing Gaussian answers really gives us all the sophisticated physics that we know for the Kondo problem, and that allows, let's say, to study quite effectively rather challenging problems. Okay, and I guess as a preview, so in the next, so we'll continue and show how this can be extended to the problem in which which is sort of an ancestor of the Kondo problem. The problem, which we said is an Anderson impurity problem, we have a localized level, which has on-site interaction, has electron phonon interaction. But that will be tomorrow. Thank you. So this is sort of the most familiar regime where all of the J's are. Okay, so there is a subtlety which maybe if you is often not appreciated. So if we have this coupling, so I have J parallel and J probe. Now notice that in this plot I allow for J parallel, right, this coupling SCSV to be either positive or negative. But say for J probe, I only show the positive value. So why is that? Something that, a trick which is often used in magnetism. So actually, you can always make a trick. You can always change the sign of x and sy. You can always choose two components of your spin and change their sign. Because this doesn't change the commutation relation, right? Because if Sx and Sy change sign and their commutation still gives me the same as Z. Or let's say commutation as Z as Sx gives me Sy. But again, if I change the sign of Sx, I get the I change the sign of Sy. So therefore, the sign of J prop actually doesn't matter, right? They can always change it. And that's why, by changing the sign of Sx and Sy, that's why it's only important to sort of show positive values of J prop. Therefore, basically, so when we distinguish between ferromagnetic and antiferromagnetic, it's really just the sign of J paradox that matters. So therefore, everything on the left of this line, on the left of this point 0, is ferromagnetic. Everything on the right is antiferromagnetic. However, if we do the actual, so let's say then if we can say that, let's say on this part, let's say including this part 2, that's a conventional regime where we have both J's are antiferromagnetic. So that's a regime where system flows towards strong coupling. What, like on the left is more surprising, right? Because here we're saying, oh, it is antiferromagnetic regime. But however, in the system, the RG flow is sort of first, okay, it's ferromagnetic. If it was perfectly SU2 symmetric, the system would flow to 0. And basically, it would mean that, that's the usual assumption that ferromagnetic coupling to the impurity spin just doesn't matter. But that's only true if it's perfectly SU2 symmetric, or if coupling to a Z component is larger than J perpendicular. Again, in this case, J flows to 0. But if coupling to like XY coupling is larger, you see that it first flows down, so it's irrelevant, but then shoots up with opposite sign. So the phase 2 from this point of view is sort of more conventional, where you just immediately start going down when magnetic coupling increases.
Any questions?
What?
Maybe Eugene will have a question.
I rest my case.
Yeah.